Example 3, find the integral of 1 over x squared times the square root of x squared plus 4 dx. Solution. Let x equal 2 tangent theta, and theta is greater than negative pi over 2, but theta is less than pi over 2. Then dx equals 2 secant squared theta d theta, and the square root of x squared plus 4 equals the square root of 4 times open tangent squared theta plus 1 close equals the square root of 4 secant squared theta plus 2 times the absolute value of secant theta equals 2 secant theta. So we have the integral of dx over x squared times the square root of x squared plus 4 equals 2 secant squared theta d theta over 4 tangent squared theta times 2 secant theta equals 1 over 4 times the integral of secant theta over tangent squared theta d theta. To evaluate this trigonometric integral, we put everything in terms of sine theta and cosine theta. Secant theta over tangent squared theta equals 1 over cosine theta times cosine squared theta over sine squared theta equals cosine theta over sine squared theta. Therefore, making the substitution, u equals sine theta, we have the integral of dx over x squared times the square root of x squared plus 4 equals 1 over 4 times the integral of cosine theta over sine squared theta d theta equals 1 over 4 the integral of du over u squared equals 1 over 4 open negative 1 over u close plus big C equals negative 1 over 4 sine theta plus big C equals negative cosecant theta over 4 plus big C. We use figure 3 to determine that cosecant theta over 4 plus C. We use figure 3 to determine that cosecant theta equals the square root of x squared plus 4 over x. And so the integral of dx over x squared times the square root of x squared plus 4 equals negative the square root of x squared plus 4 over 4x plus big C. Sidebar, figure 3, tangent theta equals x over 2, and you see the graph. We have a right triangle in figure 3. There is an angle theta. The adjacent is 2, the opposite is x, and the hypotenuse is the square root of x squared plus 4. Example 4. Find the integral of x over the square root of x squared plus 4 dx. Solution. it would be possible to use the trigonometric substitution x equals 2 tangent theta here as in example 3, but the direct substitution u equals x squared plus 4 is simpler, because then du equals 2x dx, and the integral of x over the square root of x squared plus 4 dx equals 1/2 the integral of du over the square root of u, equals the square root of u plus big C equals the square root of x squared plus 4 plus big C. Note, example 4 illustrates the fact that even when trigonometric substitutions are possible, they may not give the easiest solution. You should look for a simpler method first. Example 5, evaluate the integral dx over the square root of x squared minus a squared, where a is greater than 0. Solution, we let x equal a secant theta, where theta is greater than 0 but less than pi over 2, or theta is greater than pi but less than 3 pi over 2. Then dx equals a secant theta tangent theta d theta, and the square root of x squared minus a squared equals the square root of a squared open secant squared theta minus 1 close equals the square root of a squared tangent squared theta equals a, the absolute value of tangent theta equals a tangent theta. Therefore, the integral of dx over the square root of x squared minus a squared equals the integral of a secant theta tangent theta over a tangent theta d theta equals the integral of secant theta d theta equals the natural log of the absolute value of secant theta plus tangent theta plus big C. The triangle in figure 4 gives tangent theta equals the square root of x squared minus a squared over a. So we have the integral of dx over the square root of x squared minus a squared equals the natural log of x over a, the natural log of the absolute value of x over a plus the square root of x squared minus a squared over a plus big C equals the natural log of the absolute value of x plus the square root of x squared minus a squared minus the natural log of a plus big C. Writing big C sub 1 equals big C minus the natural log of a, we have equation 1. The integral of dx over the square root of x squared minus a squared equals the natural log of the absolute value of x plus the square root of x squared minus a squared plus big C sub 1. Sidebar, see figure 4. Where secant theta equals x over a, and we have a right triangle with an angle theta. The adjacent is a, the opposite is the square root of x squared minus a squared, and the hypotenuse is x. Back to the text. Solution 2, for x greater than 0, the hyperbolic substitution x equals a cosine hyperbolic t can also be used using the identity the hyperbolic cosine squared y minus the hyperbolic sine squared y equals 1. We have the square root of x squared minus a squared equals the square root of a squared, open the hyperbolic cosine squared t minus 1, close, equals the square root of a squared, the hyperbolic sine squared t equals a sine hyperbolic t, since dx equals a sine ht dt, we obtain the integral of dx over the square root of x squared minus a squared equals the integral of a, the hyperbolic sine t dt, over a, the hyperbolic sine t, equals the integral of dt equals t plus big C. Since the hyperbolic cosine t equals x over a, we have t equals the inverse hyperbolic cosine, open, x over a, close, and equation 2, the integral of dx over the square root of x squared minus a squared equals the inverse hyperbolic cosine, open, x over a, close, plus big C. Although formulas 1 and 2 look quite different, they are actually equivalent by formula 3.11.4. Note, as example 5 illustrates, hyperbolic substitutions can be used in place of trigonometric substitutions, and sometimes they lead to simpler answers. But we usually use trigonometric substitutions because trigonometric identities are more familiar than hyperbolic identities.